Hello, everyone, and welcome to our second talk in the mini-series on Scream. Today, Luca Bertagna will share his experiences as a Scream developer. Luca's background is in applied math, computational fluid dynamics, and specifically performance portability of scientific codes on next-generation HPC architectures. Luca received a PhD from Emory University in 2014 and has been at Sandia National Lab since 2016. Thank you, Luca.
All right, thank you, Mark. Hello, everybody. Good morning. Today, I'm going to present the talk that I gave at Supercomputing in November. And for those of you not familiar with it, so Supercomputing is a conference that is held annually in the United States, and a lot of people from all over the world come to showcase their HPC results, algorithms, and developments. There's also like a vendor section. It's a huge conference. And at this conference, there's a award that is presented every year. It's called the Gordon Bell Award, which recognizes great achievement in the HPC world by groups doing usually like a very large, solving very large, challenging, and relevant problems on one of the largest supercomputers on Earth. This year, there was for the first time, there was a new category, the Gordon Bell for climate modeling applications, and E3SM won the award. And this is the presentation that I gave at Supercomputing in the final round of the Gordon Bell for climate modeling. So the title is Simple Cloud Resolving E3SM Atmosphere Model Running on Frontier Exascale Systems. So why climate modeling at supercomputing? And I apologize, like this talk was presented to a broad audience, most of whom probably have never seen climate modeling. You're all familiar with climate modeling, so some things might look obvious to you, but this is the presentation that I gave, and I want to give you the experience of what the presentation was. Anyways, back to the talk. So why climate modeling and supercomputing? So first of all, climate change is one of the biggest threats facing humanity, which makes climate modeling a very relevant and impactful problem to solve. On the other hand, climate models need to capture a variety of scales, from global circulation down to the size of a raindrop, which makes climate models very complex, and therefore they're a good candidate for high performance computing, because in general they need to solve large amount of calculations. So, in a little bit of history here. So more than 100 years ago, Lewis Richardson envisioned this human supercomputer where like a bunch of people would sit in the spherical room, and they will solve the equation for global circulation, and each of these people will solve the equation just in the portion of the Earth corresponding to where they were sitting. And they would exchange information with their person next to them, and then some clerks in the middle of the room would pass messages to other peoples around the room, creating some sort of like global information. And this is very similar to the idea of a supercomputer. Fast forward 50 plus years, and NCAR became the first official customer of Cray Research with a Cray 1 supercomputer. So from the very moment when supercomputers were just thought of, not even existing, just thought of, to the moment where supercomputers and HPC became a reality, climate modeling has been at the center of it. I guess this slide, maybe I can skip it. You're all familiar with what E3SM is. If you're not, then that will be weird. But multiple components, broad variety of time-space scales. The history of E3SM, but maybe not all of you are familiar with EAM. Well, you probably know what it is, but don't know much of the details, at least not all of you. So E3SM atmosphere model, or EAM, is the atmosphere model of E3SM, and you can, broadly speaking, divide it into two parts, dynamics and physics. So dynamics is the part that solves the Navier-Stokes equations in a rotating spherical framework. On top of that, dynamics is also in charge of solving for the transport of tracers in the atmosphere. In E3SM, in EAM, we use the high order methods modeling environment, or HOME, which decouples horizontal and vertical differential operators. On the horizontal direction, it uses spectral element, while in the vertical direction, it uses finite difference methods. The other part of EAM is physics. So physics is in charge of approximating those processes that are not resolved by dynamics. Examples include microphysics, so phase exchanges and precipitation of water; macrophysics, which means subgrid cloud and turbulent processes; radiation, so the radiative effects of the sun on the atmosphere temperature; aerosols, so cloud and radiative effects of the particles transported in the atmosphere; and deep convection, which is the thermally driven turbulent mixing of air. The discretization in EAM, I said the couples horizontal and vertical. So in terms of horizontal, we usually use what we refer to as the cube sphere. You can see it depicted on the left. You basically take a cube, draw a grid on it of quadrilaterals, and then you inflate the cube until it reaches the shape of a sphere. Inside each of these quadrilateral, you have your spectral element degrees of freedom. And then you take each of these 2D elements and you extrude it vertically to obtain a three-dimensional grid. And the process, you can see depicted on the right. You see the two-dimensional quadrilateral and with the Gauss, Legendre, Lobato points inside, and then they're extruded vertically for a certain number of levels. We refer sometimes to an individual degree of freedom extruded vertically as a column. Physics act on individual columns. So physics doesn't know about the connections between columns. It acts on an individual column. The column for physics can be the same GLL points as dynamics, or we can use what we sometimes refer to as the PG2 grid, which I depicted it at the bottom. So in green, you see the dynamics degrees of freedom. And the PG2 grid just splits the element into four, the red boxes, and it uses finite volume inside each of these four boxes. So SCREAM is a cloud resolving model. Why do we care about cloud resolving resolutions? Well, a few reasons. One is that at these resolutions, you avoid the need for convection parametrizations, which are one of the main sources of uncertainty in climate models. On top of that, resolving convection, you can reduce systemic error in precipitation because the treatment of convective storms is more realistic and it's explicit. And finally, we improve our ability to assess the impacts of climate change on water cycle, which can affect a lot of things like multiple sector of the national and international economy, and especially when it comes to agriculture and energy production. And here, sometimes they say a picture says more than 1,000 words. In this picture, you see three pictures in this plot. They're plotting the surface altitude near the Bay Area in California, and they have an increasing resolution. At the left, you see 200 kilometers resolution, in the middle 25, and on the far right 1 kilometer. So typically E3SM simulation run on at 100 kilometer scale. So we're somewhere in between the first and the second picture, while SCREAM runs at 3.25 kilometer resolution. So between the second and the third, probably closer to the third. And just looking at these pictures, you can appreciate the amount of levels that you can capture with a kilometer scale model. So SCREAM, simple cloud resolving E3SM atmosphere model, is a particular configuration of EAM and uses the following. As a resolution in the horizontal, we have 3.25 kilometers and 128 vertical levels. Dynamics is home, just like in EAM. The microphysics is implemented with P3, the predicted particle properties. Microphysics is handled by shock, simple high order closure. Radiation is handled by RT plus RRT-MGP package. Aerosols are prescribed, and as I said, being a cloud resolving model, we do away with deep convection. I want to point out that at these resolutions, using 128 vertical levels, we have around 7.2 billion degrees of freedom per variable on the dynamics grid. So tackling this huge problem on the largest supercomputers, we enter the exascale world, and in the exascale era, GPUs are king. However, CPU performance is still crucial in E3SM. We'll still want to run smaller problems on large CPU clusters, and in this context, performance portability become very important. What do we mean by performance portability? We mean the capability of a code base to run efficiently on a variety of computer architectures. Efficiently can be measured depending on the application. There are several metrics. In E3SM, we use the simulated years per day. So how do you achieve performance portability? I can think of mainly three approaches. One is using compiler directives. So you hint or force the compiler to optimize the code based on the particular backend, the particular threading scheme you have. And OpenMP and OpenACC are clear examples of this. Then there are general purpose libraries. So you delegate architecture specific choices to a library, which is usually implemented in the same language that you're using in your source code. And Cocos and Raja are example of this. And finally, we have domain-specific languages and libraries. So with these, you usually add an intermediate compilation step. So you write code in a higher level language, and then this intermediate compilation translate this code into general source code, C, Fortran, or whatever it is. And in this intermediate compilation, you generate optimal source code for the given architecture. And finally, standard compiler can take care of compiling this intermediate source code into executable code. Example of this approach are Cyclone and Grid tools, at least in the in the climate modeling world. Obviously, maintaining multiple versions of E3SM, one for each architecture, is not even a choice. So performance portability is a must in the path to exascale. So in Scream, we chose the second approach in the list before, and we used Cocos to expose on-node parallelism. Cocos is a C++ library that provides constructs to express parallelism, like the abstracting concept like execution space, execution policy, or the parallel operation. And it also provides constructs for multidimensional arrays, which abstract concepts like data type, the memory space, the layout, and so on. It supports several backends: OpenMP, CUDA, HIP, SYCL, pthreads, Serial. It's very reliable. It has a large pool of world-class developers. It's heavily tested, countless downstream apps, which means that's more testing by these apps, and it closely follows new HPC architectures. So in the development of Scream, we did some software engineering work. We rewrote all the atmosphere model in C++ using Cocos for a node parallelism. The important things that we added were hierarchical parallelism. So that means that you have a parallel kernel inside a parallel or an already parallel region. So you nest parallelism. This is implemented in Cocos with what Cocos calls team policies. These helps to maintain cache-friendly code on CPU. And in team policy, so in hierarchical parallelism, threads are grouped into teams, and they can share intermediate work, and you minimize some index bookkeeping. And it allows for large kernels, minimizing overheads due to kernel launch. The second thing we had to add for performance portability was implementing what we call a pack data structure. It's a SIMD-like data structure to enhance C++ vectorization. C++ doesn't vectorize nearly as well as Fortran. Fortran was built for array manipulations and it vectorized really well. So in C++, you kind of need to help the compiler a little bit with these kind of like data structures. And I want to point out we're not the only one that implemented packs. Cocos had them. Trilinus had something similar. They're now getting in this C++ standard. So it wasn't just a problem of E3SM. It's a general thing. And in our packs, we added support for packed conditionals. There are some parts of the code, especially in P3, which require this. And finally, we added a workspace manager, we call it, structure, which allows to use and share a minimally sized scratch memory within parallel loops. There were also algorithmic innovations within this project. So in dynamics, we added a discrete Hamiltonian formulation of the non-hydrostatic equations, which combined with mimetic horizontal discretization ensures and mimetic vertical discretizations ensures mass and energy conservation. We implemented a horizontally explicit, vertical implicit, implicit explicit Runge-Kutta method for time stepping. We have a multi-tracer semi-Lagrangian transport with mass conservation and monotonicity preservation. And finally, physical parametrization ran on a lower resolution grid compared to dynamics, roughly 2.25 times less. That's the grid that we referred to earlier as PG2, which wasn't there until a few years ago. So the first result I want to show you is a strong scaling on of the model at a high at a lower resolution, in particular 110 kilometers. And the reason why I want to show this is because we rewrote the code in C++, but we want to make sure we didn't lose performance on CPU. So on the plot on the right, you see a variety of architecture. The red one are all GPU architectures. The blue one are C++ on CPU, and the black one are original Fortran on CPU. As you can see on CPU, we are as efficient as the original Fortran, or even a little better on the Epic CPUs. And on GPU, you can see that when you have a large workload per node, so at a low node count, we're like probably 8 times faster than a CPU per node. This is a single node which includes 4 GPUs for A100, 4 GPUs for MI250, and 6 GPUs for V100. So these were like Summit nodes, Perlmutter GPU nodes, and Frontier nodes. You can see that as you strong scale, the performance starts to taper off, and the advantage of a GPU starts to become smaller and smaller, which is an important thing when you plan your simulations. You need to give enough work to the GPU in order to make using the GPU worthwhile. So on CPU, you achieve like the scaling limit is achieved around that 1 element per core. While on GPU, the performance starts to deteriorate once you start to have less than 200 elements for each GPU. And we can run on a variety of architectures. You can see like all CPUs and like 3 different types of GPUs, both NVIDIA and AMD. And finally, this is the important plot, and this is what gave us basically the Gordon Bell Award. So I'm plotting a strong scaling of the whole screen at a 3.25 kilometer resolution. There are 2 plots here. On the left is performance of just the atmosphere, and on the right is the full model, which includes also the coupler, coupling with a surface, and then the other components. On the x-axis, you see the number of frontier nodes or summit nodes for the red curve, and on the vertical axis, you see simulated days per day. So the yellow line marks the 1 simulated year per day barrier. So there's 2 lines for frontier, blue and red. Sorry, blue and green, and the red line is for summit. So the reason why we have 2 lines for frontier is because we added some ad hoc GPU optimization, which we're trying now to integrate in the main version of the code without deteriorating other architectures. And those extra optimizations for frontier gave us a little boost across all node counts. So the takeaway here is that Scream is the first global cloud resolving model that runs on an exascale computer at cloud resolving resolutions, breaking the 1 simulated year per day. And that is a big deal. And we can run both on AMD and NVIDIA GPUs. So this is not just tailored for one architecture. Even without the frontier specific optimization, you can see that the strong scaling limit for the full model were above the 1 simulator year per day barrier. So, but it's interesting to notice that this was not just a Gordon Bell exercise, so to speak. Scream is actually is used for climate science simulation. So we completed a simulation campaign for the Diamond intercomparison project, which is used for comparing initial for model intercomparison and initial model fidelity assessment. It's a set of 4 simulations, one per season of 40 days. Then we just finished late last year the Potter's climate sensitivity simulation, which used to estimate sensitivity with respect to an increased sea surface temperature, and it's a pair of one simulation, 1 year simulations, one control run, and one with increased sea surface temperature. And then we're about to start an atmosphere model intercomparison project, which is a pair of multi-decadal year simulations to study atmosphere internal variability in extreme events. So all cloud resolving benchmarks in our Gordon Bell submissions use the same model configured exactly as in the Diamond, CESPOTTER, and AMIPS simulations. Maybe changing some parameters for the parameterization, but the code that runs is exactly the same in the exact same resolution. And finally, here is like a little eye candy of like 2 cyclones. The top image in both left and right is the one obtained with Scream, and then the bottom one is one obtained from satellite images. And you can appreciate the amount of details that this kilometer scale Scream models is able to capture. So just to conclude, real quick, Scream, that's the main takeaway. Scream is the first GCRM that runs on an exascale computer, breaks 1 simulator year per day at less than 5 kilometer horizontal resolution, and can run on both AMD and NVIDIA GPUs. And we're working on Intel preparing for Aurora. Our Gordon Bell configuration is used for important simulation campaigns and will help answer important modeling questions. So E3SM, with this effort, has established itself as a reference point for other atmospheric code bases when it comes to exascale performance. Future models that will run at exascale at a cloud resolving resolution will have to compare their result with what E3SM achieved. The takeaway is that COCOS is an efficient strategy to map the current architecture as well as reducing disruption from future ones. Porting the code to NVIDIA GPUs at the beginning, when we ported the die core, the dynamics, took some time, but adapting to AMD's still took some time, but comparing to the original one was much less. Most of the work was done with the first ported GPU. COCOS efficiently reduced disruption from AMD. And finally, that's the drawback is the C++ syntax is much heavier than Fortran, and that can be a barrier for domain scientists. This calls for good software design to separate concerns and increase productivity, and also keeping the code base maintenance manageable. And that's it.
Wonderful. Thank you.